Hello class, this week we'll be going over correlation and prediction. Here are the objectives. First, to calculate statistics to understand the relationship between variables. Next, to calculate and interpret the correlation coefficient and the standard error of estimate. Next, to use scatterplots to interpret the relationship between variables. And lastly, to differentiate between simple and multiple correlation. First, you should know that the correlation coefficient, or a lowercase r, ranges from -1 to 1. And a negative number does not necessarily mean it's bad. And you'll see this in the next slide. But you should also know that an r of 0 indicates that there's no relationship between two variables. So as you can see here, on the left side of the screen, you have -1, and it shows perfect correlation, and on the right side of the screen, you see 1.0, and that also describes perfect correlation. So here we see a scatter plot, and a scatter plot is basically a graph that has the different points of your data represented here by these just these little points. So this graph is telling us that the more number of pull-ups you complete, you'll also complete more chin-ups. So there's a direct relationship here. In the next slide, we have a scatter plot between body weight and pull-ups. And this shows an indirect relationship because as body weight goes up, the number of pull-ups starts to decrease. Lastly, we have the scatter plot of zero correlation. Here, all these plots are just randomly placed on here. So there's no real line or pattern that you can follow. So this would mean that r equals 0. Okay, we'll skip ahead to coefficient of determination. Calculating r you'll do as part of your assignment, so I won't go over that. And you won't have to do it by hand, you'll use Excel software. So here we have a little illustration of coefficient of determination. And basically, in order to calculate this, all you have to do is square your r value. And it represents a proportion of shared variance between two measures. So essentially, how much does one measurement account for the other? A good explanation of this you can find on page 60. And the author here tells us, to understand shared variance, let us examine a specific example. If correlation between a distance run and VO2 max is r equals 0.9, if you square that, you get 0.81. And if you turn that into a percentage, multiply it by 100, it's 81%. So essentially, what it's saying is that 81% of that VO2 max score can be accounted to that distance run. The other 19% could just be by chance. And your author explains this as residual error, and we'll get into error a little bit later on in this slideshow. Alright, so we want to talk about limitations of R. There are 3 of them noted by the author here. The first is that a curvilinear relationship may throw off what R actually means. A curvilinear graph would look like this, and R would be 0 in this case. However, if you just saw R as 0, you would think that the dots are all scattered around and that there's no pattern, but in fact there is a pattern. As arousal increases up to a certain limit, so does performance. After a certain point, if you keep increasing arousal, then you start seeing some negative effects. So it can be hard to tell what's going on with the data by just looking at the figure of R. The scatter plot is really important. The next limitation is that correlation does not necessarily indicate cause and effect. And you're going to hear this for prediction as well. To actually prove cause and effect, it takes a lot more than just a few statistics. You're going to see it takes a lot more. It will be explained a little bit later on, but for now, just know that correlation, so proving that one thing is related to another, or one variable is related to another, does not prove that one causes the other. Lastly, variance or range of the variables can greatly influence R. And if you read your text, the author goes on to show a figure on page 62, and it describes a little bit about how this the variance of your data can influence R. So the greater the variance, the greater the R. And this is just he basically says that the take-home message is that the value of R goes beyond or the interpretation of the value of R goes just beyond noting what the magnitude of R is. Next, we move on to prediction. This can be a very useful statistic when one variable is highly related to the other. And as it says in the second point, to some degree, one will be able to predict the other and vice versa. And again, prediction does not mean cause and effect. So still we're staying with that tenet that just because these two are highly related and one can predict the other, it still does not mean that one causes the other. And how are we going to do this? Well, we're going to do this through simple geometry. So just like you plot a straight line, that is the way that we're going to test prediction, or that's the way we're going to calculate prediction. Through simple linear prediction, also called regression. Okay, calculating regression is not, for some of you it may be pretty easy, but for most people it's not really easy. If you look at this equation and also the breakdown of the equation, it gets pretty complicated. But fortunately, in your textbook, it gives you a nice little breakdown. So if you look on page 58 and page 64, those are the two pages where this equation is broken down. The author goes on to give you an example. So first of all, you have to be able to calculate B and C, which he does on page 64. So let me skip forward here. So he calculated B and C, which is this figure here, negative 0.128 and also 25.88. And he's using the numbers from page 58, table 4.1. He's using the body weights there, the chin-ups, and the pull-ups. So the author took all the figures from table 4.1, calculated B, and then he also calculated C. For B, he came up with negative 0.128, as I said before, and for C, he came up with 25.888, and then calculated regression. He came up with 7.97 based on a 140 pound person. So essentially, he plugged in. He said, "Okay, what's the prediction of how many pull-ups someone that weighs 140 pounds can do?" By putting in 140 in x, that's what the independent variable is. The dependent variable would be estimated to be 7.97 pull-ups, and that is shown here. So for a 140-pound person, he estimated 7.97 pull-ups. And with any estimate, such as a prediction, there's going to be error. So the errors in predicting, in this case, they represent a pure error. It lets you know that the independent variable doesn't predict a portion of the criterion. And finally, they could represent a pure measure of a trait with predictor statistically removed. In this case, the true score for a 140-pound person was 12. The predicted score was 7.97, so there was about a 4-point difference there. So the the prediction can tell us, it can give us an estimate of um, what to expect, but then once you have the true score, you can, if that score, this error is positive, it's telling you that the person's true score is going to be a positive residual of what was predicted. Right, a few other things to note from this chapter. The next one is standard error of estimate. So this is like standard deviation, but for error, and it just lets you know it reflects the average amount of error in the process of predicting y from x. So predicting your dependent variable from your independent variable. And finally, the last term you should know is multiple regression, which is a complex prediction of y because it comes from more than one predictor. So the equation for this is a little bit more complicated, which the author doesn't really get into, but that would be the difference between just regression and then multiple regression. All right, moving on to chapter 5, Inferential Statistics. Make sure that you're very familiar with these terms: scientific method, hypothesis, population parameter, sample, and statistic. When I give you feedback on your papers or any assignments, you'll see me talk about target population and then also samples. So population is everyone who you're trying to relate your data or your study to. So if you're talking about athletes, well, sometimes I'll ask you to be more specific. What's your real target population? Is it all athletes? So that could mean, you know, kids in T-ball and Pop Warner football, all the way up to NFL. Or it could mean collegiate athletes. That could just mean, and that could be split up even further: NCAA D1 athletes or D2 athletes, or just anyone of college age playing sports. And then when you talk about sample, that's a subgroup. So that means the people that you're actually going to test. So if you wanted to test bicep strength in all collegiate athletes in the United States, that would be the population, but that would not really be feasible. Like, could you really go out and sample every single college athlete in bicep strength? It's probably not possible. So your sample will be a part of that population. It might be just the athletes from the institution that you go to school to or the institution that you work at. That would be considered a sample. You start writing hypotheses. This is going to be your scientific writing. This is where you're going to be very explicit about how you describe what you're actually testing. It can't be vague at all. It has to be very specific. So research hypothesis is what you believe will occur. What you have to be very familiar with is a null hypothesis. It's a statement that there is no relation, meaning if you thought that a certain drug would help you increase strength faster than someone who wasn't taking the drug, but you guys are still doing the same resistance training, then the null hypothesis would say that there would be no effect, saying that after, let's say, 3 weeks of taking this drug and doing resistance training for both groups, one taking the drug and one taking a placebo, there would be no difference. On the other hand, the alternative hypothesis would state that there is a relation. So this is how you describe that whatever drug you're testing, whatever treatment you're testing, will have an effect for the people that are actually taking that drug or doing that type of treatment. Another aspect to note is that when you're going through your study, what you're actually testing is a null hypothesis. You want to be able to say at the end of your study that this hypothesis that goes against what you think is incorrect. So you want to be able to reject the null hypothesis in most cases. Sometimes the wording may not work, may not fit correctly in that manner. It may not make sense. So in some cases, you'll see studies that actually want to accept the null hypothesis. Next, let's talk about statistical significance. So this is what we will need in our studies to be able to say that whatever results we were able to ascertain from this study were not by chance. That's one of the biggest things that will it will give you more credibility. If you're able to, tell people with with certainty that whatever treatment, whatever intervention, whatever drug you tested and that you gave to your patients actually worked, and it wasn't just by chance, then the better, the more accepted your study will be. In this case, we like to talk about alpha levels. Alpha level is, uh, like it says down here, conventionally set at 0.05 or 0.01. So it's for a good study, a peer-reviewed study, that's about where the alpha levels are usually set, is 5%. So basically saying that there's less than 5%, or sometimes at 5% or less, of the results happening by chance. When interpreting your data, there is a chance of error as well in just describing what your data is actually saying. And that's why we have these types of errors, type 1 error and type 2 errors. In type 1, as a researcher, you looked at your data, or maybe you calculated your data incorrectly, and you rejected the null hypothesis. So basically you said that your research question or your research hypothesis was correct and that the null hypothesis was incorrect, when in fact the null hypothesis was correct. So you had to say that there was no difference between groups, there was no difference between treatments. Type 2 error is when you think your intervention or your drug didn't make a difference, so you accepted the null hypothesis, but in fact you should have rejected the null hypothesis. That is a type 2 error. Alright, I want to skip over to the overview of hypothesis testing and inferential statistics. Here it breaks down what a full study would look like in 5 steps. First, to develop a research hypothesis about the relation between variables. Next, to state a null hypothesis. Third, to state an alternative hypothesis. And finally, gather data and analyze them based on this research question and the types of variables. And finally, to make a decision based on the probability of the null hypothesis being correct given the data you have collected. So as you go through this slideshow on your own, you're going to see that there's several examples, but I wanted to give you an example from real life. So this is the study that I'm going to be conducting in the next few months. So my research question, or actually just one of them, is what is the cross-education effect on the non-trained upper extremity of overhead collegiate athletes after 3 weeks of strength training the dominant arm or the non-dominant arm on the contralateral side compared to control? So this may seem a little confusing, and I actually explained a little bit about my study in last week's discussion board. So if you want to read that, it's up there. But basically, all I'm doing is having um, water polo and volleyball players do external rotation strengthening exercises for 3 weeks on one of their shoulders only. And I'm going to test their strength on the other arm, the arm that's not being strength trained, before and after this 3-week training. And so that's the question, what's going to happen? Is there going to be a difference before and after on that non-trained arm? And then compared to a control, obviously. A control meaning this group will not be doing any of the training. So the null hypothesis says there will be no difference in external rotation strength after 3 weeks of unilateral shoulder strength training on the contralateral shoulder between the DA, NA, and control groups. However, my alternative hypothesis, so this is what I want to really happen, is after 3 weeks of unilateral shoulder strengthening, the DA and NA groups will experience an increase in external rotation strength on the contralateral shoulder compared to the control group. Alright, so how am I going to analyze this? Well, the most basic way is the one-way ANOVA. I'm probably going to run some other statistics as well, but just for the purposes of this class, the one-way ANOVA is the main statistic that I'm going to use. My dependent variable being shoulder external rotation strength, my independent variable having 3 different levels because of the 3 different groups. Finally, what I want to be able to say at the end of the study, I want to be able to reject the null hypothesis, which says that there will be no difference between groups after the 3 weeks of training. So hopefully, at the end of my study, I'll be able to to reject this null hypothesis. Next, for you guys, the statistical technique that you're going to be choosing can be determined pretty easily with this table here. So it gives you all of the independent variables here, or the possibilities of the situation, depending on your independent variable, and then also on the dependent variable. So it then gives you which statistical test to use. And the rest of these slides go through an example of each one of those. So go ahead and take a look at those. Make sure that you're very aware of what situation requires what test. If you have any questions on any of this, you can email me or post it on a discussion board. I know you guys are working on your critical assignments, so this is very related to that. Eventually, we'll get to the statistical part of that. But if in the meantime you do have questions regarding statistics and your critical assignment, please send me an email so we can discuss that further. I'm pretty sure I gave everyone feedback on their critical assignment. They all look pretty good. They all look like they're going to be promising studies. But I just want to make sure that you guys are feel confident in them, and that you're finding enough research on it. Okay, so you guys have a great week, and I'll talk to you guys later.